Replication gives you copies. Every replica holds all the data. That solves availability and read throughput, but it doesn't solve the problem of having too much data for any single machine to store or process. Partitioning solves that. Also called sharding, partitioning means splitting a large dataset into smaller subsets and distributing those subsets across multiple nodes. Each node holds only a portion of the total data. Instead of one machine with a 10 terabyte dataset, you have 10 machines each holding 1 terabyte. Instead of one machine handling 100,000 write operations per second, you have 10 machines each handling 10,000. The book uses different systems names for this concept to establish that they all mean the same thing: shards in MongoDB and Elasticsearch, regions in HBase, tablets in Google Bigtable, nodes in Cassandra, vbuckets in Couchbase. The terminology varies. The idea is always the same: break the data into pieces and spread the pieces across machines. But here's the goal that's surprisingly hard to achieve: spreading data and query load evenly. If one partition gets significantly more data or more queries than the others, that partition becomes a bottleneck. The book calls this a skewed partition. And a partition that is disproportionately loaded is called a hotspot. The ideal is perfectly even distribution, all partitions roughly equal in size, all partitions handling roughly equal query load. In practice, achieving this requires choosing the right partitioning strategy for your data and query patterns. And choosing wrong creates hotspots that can make a system perform worse than an unpartitioned single machine. Partitioning is almost always combined with replication. Each partition is assigned to a primary node, but copies of each partition also live on other nodes as replicas. So a 6-node cluster might have 3 partitions, each partition with a primary on one node and replicas on the other 2. The two concerns are independent: replication governs durability and availability, partitioning governs where data lives. The most intuitive way to partition a key-value dataset is to divide the key space into contiguous ranges and assign each range to a partition. Think of a set of paper encyclopedias: volume AC, volume DF, volume GI. Each volume covers a continuous range of the alphabet. You know which volume to pull from without any lookup table. This is called key range partitioning, and it's used by Bigtable at Google, HBase, RethinkDB, and MongoDB before version 2.4. The advantage is clean range queries. If you want all sensor readings from March 1st to March 31st, and the key is a timestamp, all those readings are in the same partition or in a small number of adjacent partitions. You query one range, you get one partition. Compare this to spreading data randomly. A range query would have to scatter to every partition simultaneously. But key range partitioning has a significant weakness: hotspots from sequential access patterns. Consider a sensor network where measurements are keyed by timestamp. Sensors write continuously. All the newest data has keys in today's timestamp range. That means all writes are going to the same partition, the one that owns the current time range. While yesterday's partitions sit idle, today's partition is absorbing every single write. You've created a hotspot by design. The standard fix is to use something other than the raw timestamp as the partition key. For example, prefix each key with the sensor name. Sensor A's data goes to one set of partitions, sensor B's to another. Writes distribute across partitions proportional to the number of active sensors. But now a range query for all readings from March 1st has to query every sensor's partition separately and merge the results. This trade-off between write distribution and range query efficiency is fundamental to key range partitioning, and choosing the right partition key requires understanding your dominant query patterns. Before moving on to hash partitioning, it's worth being precise about how partitioning and replication interact, because they're often conflated but are genuinely independent concerns. Replication answers: how many copies of each piece of data exist, and where? Partitioning answers: which piece of data lives on which node at all? In a partitioned and replicated system, both questions are answered simultaneously. The book gives a concrete picture: each partition has a leader on one node and followers on others. A single node might be the leader for some partitions and a follower for other partitions. Take a 6-node cluster running 3-way replication with 4 partitions. Each partition has 3 replicas. Node 1 might be the leader for partition 0, a follower for partition 1, and a follower for partition 2. Node 2 might be the leader for partition 1, and so on. Every node is active. Every node serves both reads, for the partitions it hosts, and write coordination, for the partitions it leads. This separation matters architecturally because you can tune the two independently. You can increase the replication factor from 2 to 3 without changing how data is partitioned. You can rebalance partitions across nodes without changing the replication topology. The concerns are orthogonal. It also matters for understanding failure behavior. If the leader node for partition 0 fails, that partition's follower takes over as the new leader, just like the leader failover process from chapter 5. The other partitions on the failed node elect their own new leaders from their own follower sets. Failure of one node causes failover in multiple partitions simultaneously, but each partition handles its own failover independently. The two strategies for actually assigning keys to partitions, key range and hash, are what Chapter 6 centers on. Key range we just covered. Hash is next, and it solves key range's hotspot problem while introducing a new limitation.